All right, well, thank you very much for the opportunity to speak. By way of introduction, my name is Derek Ruths. I'm the Chief Data Scientist of Ruths AI. My last name is Ruths. I'm also Troy's brother. We're also academic brothers through Louai, who is our PhD advisor. A lot of connections there. I'm also a professor of computer science up at McGill University. What I wanted to talk about today, so the theme that we've been touching on is uncertainty. And what I wanted to really bridge was this idea of the connections that exist across data science. Part of the theme of this series ongoing is that actually as a community, as a broad data science community, we share a lot in common. And a lot of that is reflected in the methods that we use. Even though the problem domains that we work on may be different, whether it's cancer or cancer modeling or oil and gas, a lot of the techniques that we use are very similar. And so I wanted to sort of explore that idea very quickly by talking about a technique that is rampantly used currently in a lot of different places, but goes by different names, but performs very similar functions. And that is lookalike modeling. And I want to talk about lookalike modeling in the context of uncertainty. So we've all experienced lookalike modeling because we are lookalike modeled all the time on Netflix and Amazon and Facebook whenever recommendations are made. So if you log into Amazon and Amazon somehow shows you, you own an iPhone and it somehow finds out that it should recommend an iPhone charger to you or a Fitbit watch, and it seems like a reasonable fit, it's almost certainly the case that you've been lookalike modeled. And fundamentally, the idea behind that is that Amazon needs to figure out what to recommend to you. And it doesn't necessarily have all the information about who you are and the things that you like, but it knows kind of what you've purchased in the past. And so naturally what it's going to do is it's going to say, well, I have all of this information about what other people have bought. Maybe I can use all that information in order to make some inferences about you. And so when I log into Amazon, Amazon says, well, what should I recommend? Well, Derek has bought this electric scooter and this iPhone charger and this book. What should I recommend to him? Well, it can say, oh, well, let me look at all the other people who have bought similar things, who browse the similar way, and I'll just recommend those things. So that's what lookalike modeling is. And lookalike modeling has a very strong parallel, actually, in the oil and gas industry. So in the context of Amazon, we're looking for other users that are similar to me. In oil and gas, when we are looking at drilling a new well, trying to pick a site, often what we're interested in is figuring out the way that we would actually like to drill that, the way we need to operate it. Well, we don't necessarily have information about the site that we've looked at, but we need to make some informed guesses about what we should do. What are our choices? Well, one of the options is to look for other wells that we've already drilled that might tell us something about the way we should treat this new site. And so analog well identification is a really valuable capability to have. And so here I'm just sort of by way of graphics, I'm just showing sort of, you may have all these wells, you may be looking at a new site here. Well, what can you do? Well, maybe you can actually pull some of the wells in the nearby area. Maybe you can pull wells that have similar rock formations and make some guesses based upon that. And that's effectively lookalike modeling. You're effectively saying, I have something, I'm going to make some judgments, I'm going to make some predictions based on things that look very similar. But what is lookalike modeling like? How is it actually done? One of the methods that is typically used and very commonly used is KNN, which is KNearest Neighbors. And it's a very, very simple algorithm. It's simply the idea of taking the point that you're interested in this case right here, and finding the neighbors that are closest to it. Now that doesn't necessarily mean in geographic space. That could be in a lot of different feature spaces. What's important is that you're finding things that are very similar. So in the case of, we're going to look at an example here. In the case of Amazon, you might be interested in my personal attributes that you can infer. You might be interested in sort of how engaged I am in fitness, or how large my household is, or how old I am. Those are all things that could allow you to find people who are similar to me. And so what you're doing then is KNearest Neighbors is simply looking at the nearest people to you in space. Now, where does uncertainty get involved in this? Well, we'll take a look at it in a minute, but our ability to actually estimate these features is not necessarily guaranteed. Not necessarily guaranteed. We can say that, oh, as Amazon, I have this user, and this user is, I think that this user is 38 years old. But we're almost certain to be wrong about exactly that unless they're literally putting in their birth date. We might say, oh, they're pretty interested in fitness, but we may not be able to say exactly how interested in fitness they are, and so there's going to be error in there. So what I wanted to show is effectively what happens and the errors that can crop up when we don't take into account the uncertainty and how we can actually do that. So by way of starting, I have a very small data set here of users, and I've pulled out just two features, which are, it's a fitness measure, which basically ranks the user on a spectrum of fitness interest from 0 to 1, least interested to most interested, and budget. And I've normalized that between 0 and 1. So the upper bound of this is like $1,000 spend, but basically the idea is how much are you interested and willing to spend on the Amazon platform. And then we have a new user that we want to figure out some things about. So we can situate that user in space, and what we're doing is we're interested in looking for what the most similar users are to that new user. So I'm going to draw that really quickly. This is serious experimental stuff. We're doing a presentation using a Python notebook visualization. There we are. So there's our plot of users. So every single dot here is a user, and this is the new user that we have. And we can see that there's a bunch of users that are around there. So what KNN is going to do is it's simply going to pick up the nearest users. It's going to, the algorithm is very simple. It's going to go, and we can sort of see where the similar ones are. So it's probably going to pick up that one, and that one. I'll go ahead and run the KNN analysis. And so not surprisingly, we can see I've drawn them in green here. So we can see that it's picked up basically the nearest users to that point. And that's sort of the obvious thing to do. But the challenge is that, and the issue comes in when, if we really are trying to make a prediction, if we're going to say that these are the users we should predict, we should really acknowledge the fact that there may be some uncertainty in our ability to estimate this. So in the case of fitness, for example, if we as a platform have not been selling much fitness-related material, many fitness products, that's presumably how we're estimating people's fitness. We're almost certainly underestimating it, because if I haven't had many fitness-related items for them to buy, then I really don't have very good signal about how fitness interested they are. And so it's quite possible that I'll actually be underestimating that, which means that we'll take a look at it, but that means that if we were to say that I'm estimating that they are 0.5 interested in fitness, almost certainly that means that actually they're a bit more interested in it than I would have expected. In the case of budget, it may be that it's simply noisy, that it's very hard to actually estimate that. And so if we're going to account for this, we need to take into account measurement error. And so measurement error is really what we're going to be talking about and looking at here. So I've drawn out two different measurement errors. So this is the measurement error for the fitness estimate. So this is sort of the center of my measurement. So if this is what I measure, and what we can see is that actually there's a bias larger, which means that if I say that this is where I think a user is in terms of their fitness, almost certainly they're actually more fit than what I'm seeing. In the case of budget, this is what I'm estimating. And we can see that there's a distribution, an even distribution, a Gaussian distribution around that, which means that it's sort of equally likely that I'm wrong lower or wrong higher. Whereas up here, it's much more likely that I'm wrong, and I'm wrong because I underestimated. And so the difference here is asymmetric versus symmetric measurement errors. So here, this is an asymmetric measurement error, which means that it's actually going to shift all of my estimates one direction. Whereas here, I'm going to have sort of an equal likelihood of being wrong below or above. And we're going to see that that impacts the way that my prediction works. So we can make a very easy adaptation to KNN in order to take account of this. So let me go back to our diagram. So if we think about what this means, if I'm looking at this particular point, I'm asking where it actually is. In terms of fitness, my distribution is going to say that actually everybody's a bit more fit than I actually was thinking. And in terms of budget, well, actually this point is going to more or less stay where it is because it's equally likely that I was wrong one direction versus another. And so we can incorporate that quite simply into our KNN algorithm. So this is a modification of the KNN algorithm. I won't walk through the math of it, but basically what it's doing is it's taking that distribution and it's pulling a whole bunch of different possible outcomes. It's saying, well, maybe when you measured this point, it was actually over here or over here or over here, and you're drawing out of that distribution. So wherever the distribution is really tall, that's where most of our points are going to come from. So I may have plotted it here, but actually most of the points that I sample are going to come from here. And so the KNN algorithm is going to take that into account, K-nearest neighbors. And so what do we get? Well, we can actually run our modified nearest neighbors algorithm. And we can see, so this is what we had before. This is what we got previously. But if we apply our adjustment, we can see that the K-nearest neighbors that we obtain are different. Let me just try to get these on the same screen. We can see that they're different. We can see that these users, because they were now estimated to be more fit, they're shifted off to the right because of the probability distribution. And these actually shift this way. We don't see that rendered here because this is still the representation of what we measured. But underneath the hood, we can each of these points end up slightly more fit and slightly more fit. And so these ones actually become more proximate to this, to the new user that I'm querying for. And so we find that we get different K-nearest neighbors. Now in the case of Amazon, they have millions and millions of users. They have millions of data points. So this grid is almost certainly not representative of what it looks like at Amazon. Amazon is like, this would just be filled with blue dots. And so we might say, oh, well, that's probably not such a big deal. We don't have to deal with that bias. We'll just let the data speak for itself. But the world is very different in situations where we're dealing with less data, with sparse data. As we do in oil and gas. In oil and gas, we have a lot of data when we're looking at evaluating shale plays and so forth. We do have a lot of data, but in terms of the actual number of wells that we have to sample, it looks a lot more like this world than it looks like Amazon, where there's billions of transactions that I can measure. And that really changes the environment that we're operating in. We can't just let the data simply speak for itself if there are these biases. And so here what I'm showing is it's a different data set, but effectively I'm going to run the same analysis. We're going to see more or less the same results. So I'm loading information now about wells. We have a new well we want to look at, and what I'm plotting is porosity and pyrolysis, which are two features that we might use to actually evaluate sort of the potential of a particular well that we're looking at investing in. We don't necessarily have data on this particular well, but we'd like to be able to forecast something about what we expect the output of that well to be, what the production would look like, what the investment would be in order to actually get that production. And what we can see is that if we don't apply an error adjustment, we end up with selecting these wells. But if we do apply an error adjustment, we end up selecting very different wells. And in an environment in which the decisions that we make, in which the data is sparse, and in which the cost or the investment in each decision, in each prediction is very high, taking account of these priors, taking account of measurement error and priors is really, really valuable, because this isn't about whether we're showing somebody a book on Neil Stephenson's latest book versus another bestseller. This is about, are we going to put $10 million into this site, and are we going to actually drill the well in this particular way? So there's tens of millions of dollars potentially riding on this particular decision, and so it's worth actually taking the time to account for things like measurement error, things like and things like priors. And this is not something that we actually see done. I mean, to Luai's point earlier, there is in the field of machine learning and data science, particularly when we see it in industry, this kind of statistical modeling is not applied as heavily as it could. It's not well reflected in the tools that are often used, whether we're looking at things like Excel or Spotfire. They have capabilities for doing this, but often the actual modeling, the actual statistical modeling is not easy to do, and is not often a common practice in these fields. And so really what I would like to leave you with is really two takeaways. I mean, one is that this is worth thinking about. So when you are approaching a decision, and you're thinking about the factors that go into it, it's always important to reflect on the fact that uncertainty really is present in data that you're using and in each of those features. And the other is that there are tools and there are ways of actually doing this. And part of the reason why we felt that this was such an appropriate topic is because at Ruths AI, this is really part of the DNA of what we're trying to do, and we really do try to advocate for using uncertainty and using these richer models and using data, leveraging data with a sort of a statistical sophistication as a way of really making the best decisions. And that doesn't necessarily always mean you're making the best decision, but it certainly means you're making the most informed decision, and you're making decisions that are robust. Regardless of the tools that you're using, it's always important to sort of keep these things in mind. So I'll stop there. I appreciate everybody taking the time to go on this experimental journey with me in an IPython notebook. I am very glad that it worked. But again, uncertainty is something that we can't get rid of, but it's something that we definitely can manage and we can work with. And there are tools and techniques for doing this that are not actually necessarily that sophisticated. Maybe one thing to leave you with is the length of the adapted KNearest Neighbors method, which is pretty darn short. So it's not necessarily the case that these methods have to be extremely complicated. It's simply important that we make sure that we acknowledge and incorporate the right features in when we're doing the modeling. Thank you very much. Yeah.
I have a string of like 3 questions.
Okay, I'm ready.
First of all, what's the difference between a nearest neighbor model and a recommendation engine?
Okay.
The second is, does more data make a difference? So if I have lots of data, does that matter? So is more better, or does that matter? Does that not matter? And then the third one is, in kind of very homogeneous kind of environments where everything's pretty static, is there a tendency to make mistakes because everything kind of looks the same? Whereas like Amazon has got so much data, you can find these clusters of all the same. But if everything's kind of all the same, could that lead, like when we're talking about, for example, where maybe there's a lot of similarity, how do you detect things that are different in those environments, or is there danger in that? Does that make sense?
Yeah, well, so let me come back to that third one. Yeah, let me hit them all. So what's the difference between a recommendation engine and KNearest Neighbors? So KNearest Neighbors is the beginning of a recommendation engine. So if we talk about Netflix for a minute, if I'm going to make recommendations to you, the first thing I've got to figure out is the kind of person you are, like the kind of viewer you are. All I have is your past history. So there's a number of different ways I can do this. One of them, and I mean, Netflix does a lot more sophisticated stuff than this, but KNearest Neighbors is a really good way of thinking about it. KNearest Neighbors would say, well, let me make recommendations to you based on other people who have watched similar things. Right. Now, that doesn't solve the problem 100% for them, because once they've selected those people, so if the people you are sitting with right there are going to be your proxies, I still need to figure out which movies they watched to pull out and put in front of you. So there is like an extra step where I maybe need to make a recommendation. In the case of oil and gas, it's not just that I can take those wells and say that they're all good proxies. I now need to go through the process of actually like sitting down and thinking about it. But what I've done is I've surfaced the limited universe that we're going to look at. So that's the difference between lookalike modeling and KNN. That KNN is like the first critical step. But hopefully what I've underscored is that if you get that KNN part wrong, everything else is going to be wrong afterwards. Because if what I pull are people who look radically different from you, who watch things that are completely different from you, then I have no hope of actually picking the right movies to show you.
The more I engage with that, the better the smart kids.
That's also true. So, and that comes to your second question, which is more data better? Yeah, more data is typically always better. It doesn't solve the problem, because just because you have more data doesn't mean that you aren't going to pick the wrong data to use. So it'll just mean that you've got a lot more data points that are potentially biased in the wrong way, that are misrepresentative.
If you have if you have as much compute and as much storage as you want, you can comb through all the data. Does that even matter, or would it make more sense to figure out a way to isolate a certain amount of data and comb through that, right? I guess that's more where I'm, because I mean, Amazon can literally do whatever they want with as much data as they want. Does that even make sense? Or would they want to isolate a certain amount of data and comb through that? I guess it's more like
I think the jury's still out on that, actually. So, I mean, there's a certain wisdom to using all the data that you've got. But in the end, if your interpretation of that data, the algorithmic interpretation of that data, if the data you're pulling is flawed, there's no way to escape the fact that you'll have flawed insights that come out of it. So, and particularly in a domain like like unconventionals, where actually so much of the process still has an interpretive edge to it. I think we have to be really careful about assuming that you just throw more and more data without actually equipping people to actually think about it, work with the tools and actually think about it. And so I think that it's even more important in situations like this, where the number of well points, data points that we might have at the well level is valuable, but it's not sufficient that we're just going to be able to run some unsupervised algorithm and come up with the data point. The tool is really more of an ally to the decision maker. And we have to make sure that we give them those insights, I think. And in Amazon, when they have 1 billion different data points, and they're also having to surface insights, like they're feeding recommendations every millisecond, we're not deciding to drill a new well every millisecond. So we may as well spend a bit more time making sure that we get it right.
Right, because speed isn't as much of a factor.
Yeah, well, I mean, the scales are just totally different.
Yeah, right.
So it behooves us to actually approach it differently and make use of that time that we have to do the modeling more accurately. Okay, great. Yeah.
So in your example of the fitness level being skewed a little bit to the right, so you're underestimating the fitness level, how important is it to know why that fitness level was misrepresented versus just knowing that it was measured incorrectly? Like, would it be helpful to go back and figure out, maybe the way that we're assessing fitness is incorrect, or is it just better to know that we're overestimating it by this amount?
I mean, this is where domain expertise, the question was, how important is it to know where that bias is coming from or that error is coming from? And in some sense, getting a good measurement of measurement error or priors is in some sense the same thing as having an understanding of where it comes from. It's very hard to obtain measurements of error without having a reasonable concept of where it's coming from. It kind of goes back to the talk that we had just before, where I had to go talk to the biologist to figure out what is the error that's happening and where is it coming from. And it's only when we compartmentalize that we can actually start measuring it. And so to me, when we talk about the oil and gas context, that's why domain expertise is so important. I think we're far away from getting to the point where we can just build these curves, build these error distributions with no domain understanding. I mean, having that insight is going to be critical. The question is, how do we give tools to the interpreters and to the analysts that are going to allow them to actually sort those insights out of their data? So, I mean, you can never do one without the other, is I guess what I would say. Yeah.
So instead of just moving one point, why not move the whole distribution and then understand how it affects the recommendation at the end? So let's say, so you're just moving the centroid of the certain distribution.
Ah, I see, yeah, moving the centroid. So actually what you didn't see is, and actually it's here in the method, so what I actually did is I sampled. And actually Lou, I mentioned this as well. When you start getting when you get more and more complicated distributions, you can no longer solve for exactly where the centroid is going to move, and it's not even clear that the centroid is what you would want to use. And so instead, the conventional technique, which is standard practice, is to sample heavily. Now you need to sample intelligently, but if you choose a sampling technique, you pick many, many data points, and you use that to actually judge where that data point is moving.
So in the end, you output like a list of recommendations with like a ranking.
Yes, exactly. And so we didn't get the opportunity to go into that. We were actually discussing about whether it would be good to go into that level of detail, and that would be the next step to take with this, which is here I just showed it's kind of a deterministic, the centroid moves, but what would be far more accurate is actually to take the sample and then to look at how often my recommendation included this point versus a different point, because that distribution is all over the place. So those points are popping up everywhere. Yeah.
So do you also assume that the new well, the new user, they've got the same error measurement?
So that is always the question. So there are a couple ways of approaching that. One is you can assume that they have the same kind of error, in which case you'd need to do a more a probabilistic model in order to do an assessment. You could make a judgment based upon the different measurement techniques that you used. So in this case, you might actually do some extra work in order to make sure that you were more confident that the measurement that you took was the actual measurement that you were going to use. And that way you wouldn't actually have the same level of uncertainty around that point. There's a lot of different ways to actually approach that. But it would be important to be clear about what assumption you're making, for sure.
That new user or that new well comes from the same error distribution, then everything relative.
Yeah, that's right. That's right. That's right. And often what happens is, and this may come back to your question about homogeneity, it's very rare that the data that we have has homogeneous error in it, because we use different technologies to measure it. It comes from different periods of time. The different operators. There's a lot of different reasons why the error may be different. And so one level that could be valuable to push it to is actually to sort of triage the data and to think about what are your error models for these different batches of points and to model it that way. The really cool thing about most of these sampling techniques is it's actually trivial to incorporate those as long as you have the measurement or model for that error, because really what you're doing is you're just sampling. And so the samples can be drawn from any distribution, and they can be different for every single data point, and it doesn't actually impact the underlying algorithm. Yeah.
What type of sensitivity studies can you do with this? Because in your first diagram, it showed that the kind of new point pick changes based on the number.
Yep.
K and N, and I know especially when you get to kind of very sensitive areas or a number of neural nearest neighbors that you pick, it'll be your recommendation would change drastically.
Right, so that gets to the choice of K in this case. Actually, there's two ways to interpret your question. One is it could be the question of the K that you're choosing. You can do a straightforward sensitivity analysis on that and just look for when your recommendations stabilize. That would be the typical thing to do, which is you keep increasing K until you see sort of your hockey stick bottom out, and then you're not seeing any changes, or the changes slow down, and that would probably be the K you'd want to use. But the other way I interpret your question is how would you approach the sort of the broader question of modeling that kind of the uncertainty of the method. And in that case, it would actually look very similar to this, which is that it would come around to this sort of more probabilistic approach, which is where you would sample and then you would try the method many, many, many times and look at those many different outcomes. And your sensitivity then becomes how different are the solutions that you're generating with each of those iterations. All right. Thank you very much.